What I'm going to do today is go through chapter 3. I'm going to try to do the entire chapter and get it posted. And what chapter 3 for Bushong's is the atomic structure, the development of the atomic structure, the development of the theory behind what we think we know about the atomic structure. So we're going to go through the history of it. We're going to talk about the subatomic particles that we're most interested in. There are a lot of subatomic particles, but we're just going to focus on the ones that we're most interested in. I'm going to try to wrap all this up before we get into things, into the later portion of the chapter where we talk about radioactive decay. I'm going to try to wrap it up and tie it all together and help you to understand why it is that we need to understand the atomic structure. So the development of the atomic structure started with the Greeks, and they were smart enough to realize that if you broke something down far enough, that eventually you would get to a point where you would have something that was entirely different. For them, without high-powered microscopes and things like that, it was a little bit more complicated and a little bit more difficult to determine exactly what that thing would be. But for us, it's a little bit easier. So what they said an atom was something that was uncut, meaning that you couldn't slice it down any further and it still be that same thing. But if you were to take like water, you know that water is made of 2 parts hydrogen and 1 part oxygen. And if you divide it down any further than that, then what you're going to have, if you have water, is hydrogen and oxygen. And then if you divide further than that, then you've split an atom and you've got something totally different. So the word atom just means uncut. It started with the Greeks. So the Greeks recognized 4 different things, and they called those 4 things 4 substances, and those were earth, water, air, and fire, and they could exist in 4 different states, possible states. So that was their idea of the atomic model. And that suited their purposes. And then a guy named Dalton came along, and we started to develop the understanding that atoms could be joined together to create something different. Again, water. Water is 2 parts hydrogen, which is a gas, and 1 part oxygen, which is also a gas. And when we join those together, then we create water, which is a liquid. So he came up with this idea that atoms, he didn't really know exactly how they were constructed and didn't have a solid theory, but he knew that they could be combined. And what he came up with was the idea of hooks and eyes. And you can see what he was going with if you've ever been anywhere where they've had a screen door. So with a screen door, what you do is you take an eye bolt and you screw the eye bolt into the door frame, and then on the screen door itself, there's this little hook. So this thing is sticking into the door frame, and it's hooked. If you want the door to be secure, it's not very secure, but if you wanted it to not be opened easily, you would take this hook and you would latch it over this eye bolt. So hooks and eyes, what you did was you joined your house to this screen door. And so in that way, he was the first to kind of pioneer and introduce the concept of joining atoms together. That worked for a little while, and then Thomson came along, and Thomson's idea was that an atom was basically you had a well-defined or some sort of nucleus or some sort of center. And what a nucleus means is, the definition of a nucleus is kind of like the most important part. So what a nucleus is the center or the thing that makes something what it is. And we'll talk a little bit more about that because subatomic particles go into what makes a thing what it is. So his idea was if you had this gelatinous mold and you had these plums on the outside of it, you had what you refer to as plum pudding. I've never seen plum pudding, so I can't give you any kind of firsthand account of what that looks like. But what it looks like in the picture in the Bushong book is Jello mold, maybe off of a bundt cake pan with these pieces of plum on the outside of it. So it looks kind of weird, sounds kind of weird, but what it introduced us to was the concept of a nucleus, and then on the outside of the nucleus we had electrons. And then Niels Bohr came along, And he said, well, yeah, okay, you got it basically, but it doesn't really look like that. It looks like a miniature solar system where the nucleus would be represented by the sun, and then the planets would be the electrons that orbit around the nucleus. So in that way, what we recognize still yet today is the atomic model is that thing, is that the atom has a well-defined nucleus where some of the subatomic particles exist, and that nucleus defines exactly what that atom is. And then on the outside, in orbits around the nucleus of the atom, what you have are electrons. So in the Niels Bohr model, what we have is the sun would be reflective of the representative of the nucleus, and the planets would be the electrons that go around the outside. There are some differences in our understanding of the atomic structure of the Niels Bohr model of the atom and a solar system, and we'll talk about those differences here in a bit. So Mendeleev came along, Dmitry Mendeleev came along, and he identified, it was like 58 different individual atoms. We recognize now 118, and some of those are man-made, created, lab-created atoms, but some are, of course, natural that we've discovered along the way. So the subatomic particles that we're going to talk about, we're only going to focus on 3. So there's a lot more than that, but we're just going to focus on 3 because 3, that's for the entirety of our time in the program and our education. Those are the only 3 that we really need to focus on. So I have 3. Inside the nucleus of the atom, we have 2 of those. One would be the proton, one would be the neutron, and then the electrons would be in the shells around the outside, in the orbit around the outside of the atom, and those would be our planets, so to speak. So those are our electrons. So inside the nucleus of the atom, we have 2 subatomic particles. Those will be our protons. We're going to identify the protons as being positively charged. It should be that way, not an X, but positively charged inside the nucleus of the atom. And then we've got, also inside the nucleus of the atom, we've got a neutron or neutrons, and then our electrons are going to be identified as, again, the things outside of the nucleus of the atom. They're going to be negatively charged. Now, it's important to keep in mind that the charges between protons and the neutrons, or protons and electrons, the charges between the protons and the electrons are identical. But what I want you to do is I want you to look in your Bushong book on page 39 at table 3.1. What you see in that table is that the electron has a negative charge, proton has positive charge, and the neutron has a neutral charge. I'm going to go with N for neutral instead of O because I'm going to draw protons and electrons, and they're going to be circular, and I don't want to confuse you, with 0 or O for the neutron, or 0 for the neutron for no charge, and what I'm drawing is electrons for protons for neutrons. So I'm going to use N as the symbol for our neutron. And it's not going to affect your education anywhere. The registry is not going to ask you about that anyway. So it's just for our class. So what you see in that table is a number of different things. The proton lives in the nucleus. It has a positive charge. It has an atomic mass unit and an atomic mass number. The atomic mass unit is 1 point something. Don't memorize that. It just know that it's 1 point something. So it effectively has, it's 1.007, and then, who cares? But it's 1 point something. The neutron also has a mass of about the same, or the atomic mass unit of a little bit higher. All right, so it's 1.008, and then it doesn't matter anymore either. So it's also 1. So what the atomic mass number is going to be is the rounded off atomic mass unit. So both the proton and the neutron are going to have an atomic mass number of 1. But if you look at the electron, the atomic mass unit of the electron is tiny in comparison. So if you look at the atomic mass number of the electron, it's 0. So what you've got then is the relative size between the protons and the neutrons are fairly the same. The neutron is a little bit bigger, but it's not big enough to really worry about. But both of them are gigantic in comparison to the electron. But then also keep in mind that the positive charge of the proton and the negative charge of the electron are opposites, but they're in exactly the same magnitude. And that's important to keep in mind for reasons we'll talk about here in a minute. So relative size, the protons and the neutrons are gigantic compared to the electron. Relative charges, the charges are the same. And what I want you to be thinking about is the neutron is not neutral by virtue of having no charge at all, but rather because it has both a positive and a negative charge stuck together. You know, opposites attract, right? So if you take the positive end of a magnet and you stick it to the positive end of another magnet, and then they push each other apart. So like charges repel each other, but if you put positive and negative, then they join up together. So opposites attract. So we're going to say that the neutron is neutral because it has both charges. The proton is positive and the electron is negative. So the important things to remember about the proton is that it exists inside the nucleus. It's got a atomic mass number of 1, so it's relatively large compared to the electron. It's got a positive charge, but also the number of protons determines what the atom is. So hydrogen always has 1 proton. Helium always has 2. So if you look again in your Bushong book on page 38, you see the periodic table. And in your Bushong book, what you'll see are certain things that are magnified up. So if you're looking at the one that has the W at an atomic number of 74, that is your tungsten. And we use tungsten inside the X-ray tube in the filament and also in the target. And tungsten is always going to have 74 protons. In most of your atoms, most of the time your atoms are going to seek to be neutral. So you're going to have the same number of protons as what you're going to have electrons. You're going to have the same number of electrons as what you're going to have protons. So they're always going to match, which means that they're usually going to match. And what that means is that your atom is going to be neutral. Just like the neutron, your atom is going to be neutral. It's not going to have any charge. If you remove an electron, then you've got a disparity in the number of protons and electrons. If you remove an electron, you remove a negative charge, and therefore you're going to have a positively charged atom, and then you're going to have an ion, right? So you removed an electron, you got a positive ion. If you add 1 more electron so that there's 1 more electron than protons, then you're going to have a negative ion. So your atoms are going to seek to be neutral, but you can give them a positive or negative charge. And that's not going to be by doing anything with the proton. Remember, the proton is inside the nucleus of the atom. It doesn't move. If you remove a proton, then you create something entirely different. Like, again, if you have helium and you remove 1 proton from helium, now you've got hydrogen. All right. So when we're talking about creating of ions, what we're talking about is adding or subtracting electrons. We're not doing anything with protons. Protons are always going to remain the same. Neutrons, we can have a number of different configurations of neutrons. We'll talk about those here in just a bit. But for the most part, whenever we're talking about electrification or creating a charged particle, then we're talking about movement of electrons, almost universal. So the electrons live in the shells outside of the nucleus. And what we have with the electrons is that they exist in specific orbits. So your orbits, the orbits of your electron, for whatever reason, they start with a K shell. So if you have a nucleus, that's where your protons and your neutrons live, your first shell here is going to be your K shell. So if we have one proton, let's say we don't have any neutrons, we might have neutrons, we might not. But if we have one neutron, or we have one proton and one electron, then essentially what we have is hydrogen. And it's also, neutral, right? So that's your K shell. Your next shell out is going to be L, and then M, and then N, O, and P. It's going to follow the alphabet, but it's going to start with a K shell as the innermost shell. So your arrangement of electrons, there are a few things to remember about the arrangement of electrons. First off is that the innermost shell can only ever have 2 electrons. Any of your shells, you can calculate how many electrons you can have in any of your shells with this formula right here. And that's not a Z, that's a 2. Both of those are 2. 2n squared. So n represents the number of shell that we have. So this innermost shell is our first shell. So it's our first shell. So using that, we can say 2 times 1 squared. And you got to remember your order of operation. The first thing that you do is remove parentheses. We have no parentheses. And the next thing you would do is take care of the exponent. So what we're going to do here is we are going to square our 1. And 1 times 1 is 1, right? So that's what it would look like. Our innermost shell can only have 2 electrons. This would be our second shell, so we would do the same thing, 2n squared. So in our second shell, we could have 2 times 2 squared, and that would be 2 times 4. We could have 8 in our next shell. So the next shell out would be 2 times 3 squared. So 3 squared would be 9. We'd have 18, right? So just keep on going like that. So what this tells us is that the most that we can have in any shell is 2n squared. But we can never have more than 8 in an outer shell. And it's just something you got to file away. For this class, there's no reason to dig into exactly why that is. Just file it away that you can't have more than 8 in an outermost shell. Also, though, our most stable state would be to have 8 in the outer shell. That's going to play a part in what we're going to talk about here in just a little bit. So, again, if we add or subtract electrons, it makes an ion. Proton determines the element. Neutron just adds mass. Most of the mass in the atom is going to be found inside the nucleus. So going back to what I was talking about before with the solar system, you look out at the solar system and the main thing that you see is empty space. It's a long way from the sun to Mercury. From Mercury to Mars, it's a long ways. From Mars to the Earth, it's a long ways. Venus, just on and on. It's a long ways in between the planets. I think Eric asked this question in class, and I want to show this. The question was, if our atoms are basically like solar systems, and there's a lot of space in between each one of the shells, in between our nucleus and the first shell, why are we not transparent? And that's a good question. And it really has to do with the size of the atom. Atoms are very, very small, and we're viewing them from a distance. So I'm going to bring up a picture here in a second of the Andromeda Galaxy as seen from the Hubble Space Telescope. So it's magnified up about as much as what we can see. But even in that, what we see is primarily that it's difficult to see through. So it's 2.5 million light years away, and that's what it looks like, magnified up as much as we can magnify it up. So you can kind of see through it, but it's so milky. There's millions and millions of stars and light and dust and all kinds of stuff in there, basically kind of like subatomic particles. And you just really can't see through it very well. So applying that to what we see in the tiny little bitty atoms that we're looking at in our body, and then the thickness, how, I mean, some of us are thicker than others, but the thickness of the tissue that we're trying to see through, you just can't see through it all that well. If you were to cut the tissue thin enough, you could see through it. But it has to do with how many, how small our eyes can perceive and how many atoms and the thickness of the atoms that we're looking at. We just can't see through it. We're not transparent. So I'm going to get rid of that. All right, so back to the solar system model. Mainly what we're looking at is two things in the solar system model. One is that because our atomic mass unit, atomic mass number of proton and neutron are massive, and they, compared to the electron, they both have a mass of 1 compared to 0. The electron is so small, it almost doesn't exist, right? So these are tiny, but in comparison to that, they're massive. So the bulk of the mass of your atomic structure is going to be found inside the nucleus of the atom. So just like in our solar system, the biggest part of our solar system, mass-wise, is going to be the sun. And then the planets are, of course, much smaller than the sun. So planets, little, nucleus, sun, massive, distance in between, very far. If you remember back in the last chapter, we talked about acceleration of gravity, gravity being the effects of mass on, or the weight being the effects of gravitational pull on a mass. So even though these have very little mass, they do have mass. So there's going to be a gravitational effect here. So the protons are positively charged, the electrons are negatively charged. Opposites attract. The electrons are going to be flying around the nucleus. And what we have is, because of the mass of the nucleus and the positive charge of the proton and the negative charge of the electron, they stay inside of these orbits. So we have two forces at work. One is what we refer to as centripetal force, and the other is centrifugal force. So centripetal force has to do, we can make the analogy that the centripetal force is a gravitational pull. So we've got gravitational pull holding these electrons into space, into the orbit, so that they don't fly out, as opposed to the centrifugal force would be the force that's holding them out of the nucleus of the atom. So if you've ever been to the beach as a little kid, you probably took a bucket at some point, filled it up with water or sand, and you spun it, right? And the faster you spun it, the more it stuck to the bottom of the bucket and it didn't fall out on you. But if you slowed down enough, then it'd fall out on you. Excuse me. So what we have there is those two forces together. We've got the bucket keeping it flying, the mud or the dirt or the water from flying away, but you've also got the motion of your arm kind of keeping everything from falling down on you, right? So the things that you need to know about the force that's holding our electrons into place is what we refer to, first off, as electron binding energy. And two things affect electron binding energy. One is the size of the nucleus. So remember, again, back from the last section where we were talking about acceleration of gravity, we were talking about the difference in gravity on a body on the Earth versus on the Moon versus on Jupiter. It seems like on Jupiter, the gravitational pull is 2.5 times, roughly 2.5, I think it's 2.4 times what it is here on Earth. Big planet, big gravitational pull. On the Moon, it was 1/6. So small planet, Moon, satellite, if you prefer, then our gravitational pull is not quite as strong. So we've got more gravitational pull here on Earth and on the moon, and not as much as on Jupiter. So what we take from this is the bigger the planet, the more the gravitational pull. And the same thing here. The bigger our nucleus, let's say we've got 10 protons, and we'll just forget about neutrons for now, then what we're going to have is the electron binding energy for the electrons in every shell is going to increase. So they're held in place a whole lot stronger than what they are with the hydrogen atom with the one proton. So the bigger the nucleus gets, the greater the gravitational pull, so to speak, or the electron binding energy. So they're held into place a whole lot stronger with a larger nucleus. That's number one. Number two is that the closer the electrons get to the nucleus, the greater the gravitational pull as well, the greater the electron binding energy. So think about this. If we shot a satellite up into space and it was in a low Earth orbit, then what we're going to have is orbital decay, and that satellite's going to fall back to Earth pretty quickly. But if we get it further and further away, but it's still within the gravitational pull of the Earth, it'll stay in orbit for much, much longer before it undergoes that decay and falls in. So the closer that satellite is to the Earth, the greater that gravitational pull. And the same thing here. So the two things that you need to know about electron binding energy is, one, the bigger the nucleus, the greater the gravitational pull, the greater the electron binding energy. It's one. Two is the closer it is, the greater the electron binding energy. So I'm going to refer you back over to Bushong again, and we're going to take a look at this. So if you flip over to page 45, then what you'll see is a lot of different elements. So what we see is K-shell binding energy of beryllium, for example. The atomic number for beryllium is 4. So the atomic mass is 9. What that means is it's got essentially 5 neutrons. So it's got 4 protons. The protons determine the element, so your atomic number equals the number of positive charges equals the number of protons. That determines your element. So we have 4 protons. The atomic mass number really doesn't matter to us. But if you look over at the K-shell binding energy, all the way over on the far right-hand side here, then our K-shell binding energy is 0.11. As opposed to if you come down to barium, for example, barium, our atomic number is 56. So that's 56 positive charges. That's what determines our elements, number of positive charges, number of protons. And we have 56 in barium. And if you look at the at the K-shell binding energy is 37.4. What we use in the X-ray tube is tungsten. So tungsten is represented by W. And that's because T was already taken. And the atomic number is 74. It's always going to be 74. Always going to be 74 because that's the number of protons for tungsten. So if you look over at the K-shell binding energy, you see 69.5. And that number should ring a bell for reasons I'm going to talk about in just a minute. So the inner shell binding energy for the tungsten atom is 69.5, and it's always going to be 69.5 for that inner shell, that K-shell binding energy. Now, if you look on the opposite page on 44, you see over here, you have to look at your own book. I can't hold it up well enough for you to see it. But what you see in tungsten is the K-shell has 2, because 2n squared. The K-shell is the innermost shell. There are only going to be 2 electrons, and our binding energy is equivalent to, they rounded it up, 70. The L shell, though, the next one out, notice it's got 8, but the binding energy drops dramatically. It went from, in this illustration, 70 to 12. So the binding energy dropped very dramatically. And the next shell out is the M shell. We've got 18 in it, and we've got 2.8. And then the N shell, we've got 0.6. The O shell, we've got 0.08. 8. So it drops very dramatically. So again, what we see just in this illustration here, just pay attention to the images. The carbon, the nucleus is small. K-shell binding energy is low. Even the K-shell is low, is 0.3. The L-shell, it drops significantly. So what you pick up from just that is the further the electron is away from the nucleus of the atom, the lower the binding energy. So that's lesson number 1. But then if you drop down to barium, K-shell, still have 2 in the innermost shell, the approximate binding energy that the K-shell is going to be 37. So what we've got now is a larger nucleus, right? So we got a larger nucleus, larger, higher binding energy. And then we drop down to tungsten, that K-shell is 70. Again, our atomic number went up. Our nucleus got bigger. Our K-shell binding energy is 70. L-shell drops to 12. So again, 2 things to remember about binding energy. Closest to the nucleus, highest binding energy. Big fat nucleus, higher binding energy. All right. So then we get into atomic nomenclature on page 43. So a number of things about atomic nomenclature. Some of the things that I'm going to mention here are going to be more important than others, just like everything else, really. So the atomic mass number and the precise mass of an atom are not equal. So ionization occurs whenever you add or subtract electrons. Some things are, more ionizable than other things. But if you look on page 43, you've got isotopes. So we're going to run through some definitions. An isotope is an atom that has the same atomic number. So sometimes whenever you're reading through definitions, take a break, partway through and identify exactly what's being asked. So isotope, atoms that have the same atomic number, stop. So what is the atomic number? That is the number of positive charges. Number of positive charges means number of protons. All right. So they have the same number of protons, but a different atomic mass number. Okay. So what adds to atomic mass? There are 2 things really that add to atomic mass. That's a big goose egg, right? The electron effectively has no mass. Its mass number is 0. So we're talking about the number of protons and the number of neutrons. So you have 2 atoms, let's say side by side, and we've got, let's see where I can write this. We've got 2 atoms side by side. I'm not going to draw the electrons because they don't matter here. Well, we've got 2 atoms that are side by side, and I've got one that has, let's say, 1 proton, and that's it. Okay, atomic number is 1, right? Over here, I've got another one that's got 1 proton, and it's got 1 neutron. All right, so what determines what the atom is? That would be the number of protons. So what atom has only 1 proton, and that would be your hydrogen atom. So we've got hydrogen atom, we've got 1 proton, our atomic mass here is 1, right? But over here, I've got 1 positive charge. What does positive charge determine? And again, that would be what the atom is. So is this hydrogen? And the answer is yes, because it has 1 proton. And protons, number of protons determines the atom. So it's still hydrogen, right? But our atomic mass here is 1. Our atomic mass here is 2. So let's look back at our definition of isotope. And this is all theoretic. What I'm drawing is theoretic. What I'm talking about is not. I'm just using these as examples. All right. So Isotopes, atoms that have the same atomic number but different atomic mass numbers are isotopes. So what we have here then are two isotopes of hydrogen. Okay, isotopes, same atomic number, meaning they are the same element, but they have different weights. And we'll talk a little bit more about that here in a second. Of the four things that we're going to talk about, this is most important. So isobar, atomic nuclei that have the same atomic mass number, but different atomic numbers, are isobars. Okay, so now what we've got is atomic nuclei that have the same atomic mass number. All right, stop there. Atomic mass number, we've got 2, and we've got 2. Let's see. So atomic nuclei that have the same atomic mass number, right? But different atomic numbers. Okay? So now maybe what I've got over here is one positive charge and one neutral charge. Would that give me an atomic mass number of 2? The answer is yes, because for the atomic mass numbers, we're just going to add the protons and the neutrons. Over here, though, what we've got, let's say, is we've got 2 protons. So what can you tell me about the difference between these two? They have the same atomic mass number. They've got almost the same overall atomic weight, right? They're both 2. The mass difference between the mass unit difference between a proton and a neutron, very minimal, right? So they're almost the same in that respect, but they're not the same. This is hydrogen, and this is helium. So atomic number determines the element, what it is, right? So over here we're still at hydrogen because we have one positive charge. Over here we have 2. So this is helium, that's hydrogen. Not the same. Where we're going to use that one, I'll be honest with you, we're not. Isotope will. Isotone. So atoms that have the same number of neutrons, stop. Same number of neutrons. So we've got over here, so we've got 1 neutron, 1 neutron. Atoms have the same number of neutrons, but different numbers of protons. So we got 1 proton, 2 protons. Then what we have is almost nothing the same, right? Our element's going to be different. This is still hydrogen, and this is still helium, right? There's still hydrogen and helium, but we've also got an elemental mass or atomic mass of 2 versus 3. It's almost nothing's the same. So isotone, everything is different. And then isomers have the same atomic number and they have the same atomic number and the same atomic mass number. So basically they're twins. With the isomer, you may have 2 different elements, the same element, but 2 different compounds of the same element that behave just slightly different. But basically they're twins. So they're pretty much the opposite of an isotone. Everything is the same. So let's flip back over to isotopes. So where isotopes are is that, let me flip back over to page 45. If you look back on page 45, that table right there, table 3.3, what you'll see is that they've got that column just to the right of the middle, number of naturally occurring isotopes. So you've got different atoms with a different arrangement, different number of isotopes, and really what that means is they've got a different number of neutrons. So with a neutron, the only thing that it really adds is elemental mass. Doesn't do just a whole lot aside from that, as far as we're concerned. just adds elemental mass. But the problem is that it can get so big and so heavy it becomes unstable. So if you look all the way down at the bottom, you've got uranium. Uranium, the atomic number is 92. The atomic mass number is 238, which means that it's got 146 neutrons. And that's the average. So you've got 3 different possible arrangements. And what you know about uranium is it's radioactive, right? Or it could be radioactive. So radioactivity is where we're going to spend almost the rest of this lecture. I'm going to get rid of all this. You've got it in a recording, so you can kind of back up and take a look at it if you want to. So if we have an element that becomes too big and heavy and it becomes unstable, then it's going to seek to stabilize. It's going to undergo what we refer to as radioactive decay. We have 2 different processes that might happen. We've got alpha particle emission and we've got beta particle emission. So in both cases, what it's trying to do is get rid of some neutrons. So again, these numbers don't mean anything. They don't represent any kind of element, and they're not realistic. It's just simpler to keep up with by use whole numbers or even numbers that are, multiples of 10. So let's say we've got an atom and it's got 10 protons. Now, protons in this case really don't matter. Well, they will matter, but they don't matter for radioactive decay. Now, let's say we've got 20 neutrons. So our neutrons are 20, and let's say it's unstable and it's going to undergo radioactive decay. It's going to undergo that in one of 2 ways. We're going to have beta emission or alpha emission. All right. So we're going to start with alpha emission. And what happens with the alpha emission is that we're going to break off a chunk of this thing. A great big chunk of this is going to go away. So what's going to get kicked out is 2 protons and 2 neutrons. So essentially what it's going to kick out is a helium nucleus. So it got rid of 2 of both of those, right? So now what happened is our atomic number drops to 8. So anytime we have alpha emission, this is alpha emission, our atomic number is going to decrease. So it dropped from 10 to 8, and our neutron, our elemental mass was 30. Now we've got 8 and we've got 18. So we've got 26. Our elemental mass is 26. So we've got an alpha particle floating out there all by itself, and then we've got this thing that's our new element. So if it's still unstable, then again, it can undergo either alpha or beta emission. Now, here's the thing. You remember I told you that I wanted you to be thinking about the neutron as not being neutral because it has no charge, but because it has both a positive and negative charge. And this is where this is going to come in. With beta emission, what we're going to do is we're going to kick out an electron, essentially, from the nucleus of the atom. Wait a minute. We said that the electrons lived in the shells around the outside of the atom, and they do, right? Except for if you consider the electron or the neutron has both positive and negative charges to it. So if we kick a negative charge out of a neutron, then what's going to happen to the neutron? I'll give you a second to think that over. It was neutral. You got rid of a negative charge. So then what's going to happen to the neutron? We're not going to have 20 neutrons anymore. We're going to have 19. And then we're going to have 11 protons. All right? So with beta emission, with alpha emission, our atomic number goes down. With beta emission, the atomic number goes up. All right. So I mentioned that uranium is radioactive. Not all isotopes of uranium are radioactive. There is such thing as depleted uranium. So with depleted uranium, what you've got is you've got both of these things going on, so that maybe you kick out an alpha particle and you get rid of two beta emissions, and we maintain the exact same atomic number, and our atomic mass decreases, and our number of neutrons decrease as well. So depleted uranium, happens like that. I don't remember if it's uranium or plutonium, but one of the two undergoes enough alpha emissions relative to beta emissions that is actually what lead becomes. So we can change our element, the entire element, through radioactive decay. So the question then I get every year is, what does this really have to do with diagnostic radiology? There's two things. One is that we actually use beta emitters, and there's some experimentation going on with alpha emitters in nuclear medicine. So what nuclear medicine is kind of like the exact opposite of X-ray. With X-ray, we create an external radiation beam, and we pass that beam through the patient to create a shadow on the opposite side of the patient. With nuclear medicine, what we do is we inject the patient with radioactive material, and then we measure how well it concentrates inside of the patient's body. For example, if the patient has a thyroid tumor, cancer in the thyroid, we can tag the radioactive material to stuff that would go to the patient's thyroid, maybe iodine or something like that. It would collect in the patient's thyroid, and we can measure how much radiation is coming off of that. And in that measurement, we can determine whether or not that's an abnormally high or low amount of radiation. So we can make a determination if the patient's got hypothyroidism, if too low is coming off, or possibly cancer, if too much is coming off. So we actually do use these. But in diagnostic radiology, we don't. But we use something similar. So let's go back to the first chapter. You remember Rollins. Rollins was the guy who started using filtration, right? Collimation filtration. So Rollins, through filtration and what we refer to as hardening of the beam, making the beam a higher quality by removing the low energy X-ray photons, we can better measure the quality of the X-ray beam. Kind of stumbling through this, but we can better measure the quality of the X-ray beam by its average penetrability, or what the average X-ray beam will penetrate. So what we refer to is half value layer. All right. So what half value layer is the amount of an absorber you would have to use to cut the intensity or the quantity of the X-ray that you emit from the X-ray tube in half. Right. So with half value layer, what we have is, let's say we create two X-ray beams. One X-ray beam, we're going to use the same technique on both of them. We're going to use just arbitrary numbers: 100 kVp, 100 mass, and let's say that gives us 100 MR of exposure. So we're going to use the same technique on both machines. All right, so this is maybe a brand new X-ray machine. This machine's been around for a long time. So we make an exposure with this machine at 100 kVp with 100 mass, and it gives us a 100 MR exposure. It really wouldn't. It'd give us more like 500 MR exposure, but this is just simple. All right, so let's say we take in place 1 millimeter of aluminum beneath the collimator housing, and we shoot through that 1 millimeter of aluminum. So we have 100 MR above that. if it cuts that down to the equivalent of 50 MR exposure, that is what we refer to as a half value layer. One layer of aluminum, 1 millimeter of aluminum, cut the intensity of this X-ray beam in half. Okay. Over here, what we have, let's say we've got the same setup, same technique, and we use the same 1 millimeter of aluminum, and let's say cut it down to 75. What that means is that this X-ray beam is better filtered, it's harder, so that more high energy X-ray photons were created. If they weren't high energy X-ray photons, they would not penetrate our 1 millimeter of aluminum. They'd absorb like what they did over here. So we can compare these two rooms and say this has a better X-ray, a harder X-ray, a better filtered X-ray beam than what this one does. So you might be thinking, well, how can that be possible whenever you've got 100 kVp, 100 mass giving you 100 MR? And the answer is this. Every year, we're going to have somebody come in and run quality control on our machines. What happens is that over time, our X-ray tube, our filament inside the X-ray tube will start to vaporize and coat the inside of the X-ray tube. That's what we refer to as tanning. And I mentioned tanning in class last week. And what tanning is whenever you unscrew that incandescent light bulb and you see that blackening of the glass right before the base of the where the light bulb screws in, that's basically tanning. It's vaporization of the filament that coats the inside of the X-ray tube. So if this machine has been used for a couple of years, then some of that filament is going to coat the inside of the X-ray tube with tungsten, and what that's going to do is it's going to increase the filtration, the filtering ability of that X-ray tube, and it's going to reduce the intensity. Okay, so it reduces the intensity, but at the end of the year, the maintenance guy comes in and he has to increase that intensity back up. So he has to take, at the end of the year, maybe you're not getting the 100 MR, you're getting maybe 80 MR. So he has to kind of goose the machine and juice it up to where he's still getting 100 MR. But it's going through that tungsten, which is filtering out some of those low energy X-ray photons, so that what you're left with is more high energy X-ray photons. So you do that year after year after year, and what you get is a better filtered X-ray beam that still puts out the same number of photons, but they're better photons. All right? So that's what we refer to as half value layer. Half value layer is the diagnostic equivalent to what we refer to as radioactive half-life. So radioactive half-life is where we have a quantity of radioactive material, and we measure how long it takes for that radioactive material to disintegrate to about half of its original value. You might have to calculate this on the test. All right, I'll show you the easiest way to get to it, because if you don't do it this way, you're going to have a tendency to get confused. So radioactive half-life is how long it takes for a quantity of radiation to decrease to half of its original intensity. So again, let's simplify. We have 100 millicuries or whatever of radiation off of this glob of stuff. Okay. So I mentioned that some of the elements that we use, or some of the elements in the elemental table, are man-made, and our radioactive material that we put inside of the patient are man-made radioactive isotopes. Radioactive isotope is just an isotope of an atom that's radioactive. So we use man-made because the half-life is very short. Some isotopes of potassium have a half-life of 100,000 years or more. Carbon-14, which we use to radiometric date fossils and things like that, has a half-life of 5,184 years or something like that. So what we have with half-life is, let's say we've got this quantity of radiation in this piece of stuff, and let's say that our radioactive half-life is 1,000 years. So radioactive half-life means that's how long it takes to cut our radiation intensity in half. So if we have 100, call it what you want. Let's just go make it simple. We'll go with the same thing we mentioned a second ago, MR. We have 100 MR in 1,000 years. We're going to divide that in half. How much are we going to have? Well, it's radioactive half-life. So in 1,000 years, now we got 50. All right, so that's one half-life. One half-life, cut it to 50. So a second half-life, you don't go back to your original. All right, so what you've got now is you're going to cut this one in half and cut it down to 25. All right, so that was your new quantity. That 50 was your new quantity. And in 1,000 years, now we're up to 2,000 years. We have two half-lives, and we're at 25. So how, in another 1,000 years, would be at 3 half-lives, how much will we have? Again, we would take that, divide it in half, we have 12.5. Okay, so radioactive half-life, the quantity or the amount of time that it takes to cut the intensity of a radioactive material in half. Radioactive half-life. I recommend that on the test that you work it out kind of like that so that you don't confuse it and just divide, like 4 half-lives into whatever quantity I give you. Work it out like that. Just draw you a circle, cut it until you get to however many half-lives I ask you for. All right. So radioactive half-life is to radioactivity what half-value layer is to ionizing radiation from X-ray tube. So I did skip over one thing, and that is combination of atoms. We talked a little bit about that in class on Wednesday. We've got 2 different ways we combine atoms. And I talked about covalent bonding. And covalent bonding was where we created the water. And some of your test questions are going to say, which one is specifically for sharing of electrons. Well, both of them share electrons. With covalent bonding, what you have, use the example of water. What we have is oxygen, right? With oxygen, what we had were atomic number 8. So we had 2 in the innermost shell, then we had 6 in the L shell, and then we combine that with 2 hydrogen molecules, right? We have 2 hydrogen molecules, and in that, what we accomplished was we are sharing electrons, and the purpose for the sharing of the electrons in this case was to have 8 in the outermost shell. Covalent bond. Very difficult to create a covalent bond, very difficult to split it back apart. With ionic bonding, then what you have is sharing of electrons as well, but the purpose for the sharing of electrons is to try to get to neutrality. So what you have with a ionic bonding is maybe an atom lost an electron, another atom picked it up. Now you got a positive ion, you got a negative ion, they come together and they neutralize. So table salt would be an example of an ionic bond. So ionic bonds, easy to create, easy to destroy. Covalent bonds, the purpose for covalent bonding is to get 8 in the outermost shell, very stable, but also very difficult to create and very difficult to destroy. So some definitions I've also passed up. So atoms of various elements may combine to form structures called molecules. So water is a molecule. Compound is just a quantity of any kind of molecule. Radioactive half-life I touched on. Radioactive decay I hit. So types of ionizing radiation, you got particulate radiation. Alpha particles, beta particles are both particulate radiation. And particulate radiation is what you get in like nuclear meltdowns. Fukushima, that would be an example. So with alpha particles don't penetrate very well. They're extremely toxic, or extremely dangerous, I guess is a better word. Alpha particles, the quality of the radiation, you got to wrap your mind around that. Quality of the radiation is 20 times what it is with X-ray, but it's also easy to stop. You see them wearing those paper outfits or paper gowns, paper jumpsuits whenever they're working with radioactive material, and the paper will stop an alpha particle. Won't stop a beta particle. I don't think it'll stop a beta particle. Certainly will not stop an X-ray. So again, back to the last section, not all types of electromagnetic radiation are ionizing radiation, and particulate radiation is ionizing radiation as well. So ionizing radiation is not just confined to electromagnetic radiation. And then finally, we get to pages 51 and 52, and really 51, electromagnetic radiation. We're going to spend a lot of time in the next chapter on electromagnetic radiation, but X-rays, gamma rays, any kind of visible light, anything in the electromagnetic spectrum is going to be a electromagnetic radiation. And it's just radiation that demonstrates both electric and magnetic properties. And what we call an individual piece of electromagnetic radiation is a photon. And a photon, you can kind of think of a photon as being to electromagnetic radiation what an atom is to matter. It's a single piece of electromagnetic radiation. So photon equals atom of light, let's say, or atom of X-rays. And I think that is it. So that's chapter 3, Bushong chapter 3, front to back, in a single lecture, unless I decide to break this into two.